Welcome viewers. Welcome to Physics World by Sudhakar. In the last video, we have seen how entropy is defined. Okay, change in entropy ds of any system is greater than or equal to delta Q by T. That's how entropy has been defined. The units of entropy are joule per Kelvin. Okay, delta Q is amount of heat given to the system or taken from the system. In this inequality, right, for a reversible process, ds is equal to delta Q by T. For an irreversible process, ds is greater than delta Q by T. Okay, this is the fundamental definition of entropy. N in Greek language refers to something like energy. Okay, trope means transformation. If something entropy is related to transformation of energy concept. Okay. Now, the way Clausius has defined it, change in entropy of system is like this. Okay, in a reversible adiabatic process, okay, in any adiabatic process, delta Q equal to 0. In a reversible adiabatic process, when delta Q is equal to 0, ds equal to 0, or entropy S of the system remains constant. Okay, this is what we have observed in our last video. Remains constant. Okay, right now, before further proceeding into the entropy, we will see what is known as Cardinal Theorem. Okay, right? What is Cardinal Theorem? Karna, after providing us with Carnot engine, he has given what is known as Cardinal Theorem. Okay, what does Cardinal Theorem say? In a Carnot engine, we got the efficiency of a Carnot engine as eta equal to 1 minus T2 by T1. Okay, Carnot engine is a reversible engine. For a reversible heat engine, efficiency eta equal to 1 minus T2 by T1. In general, okay, efficiency of any engine, let it be reversible or irreversible, can be written as 1 minus Q2 by Q1. This is the general definition of the efficiency of any heat engine. For a Carnot engine, which is a reversible engine, we have got eta is equal to 1 minus T2 by T1. Okay. So we have seen, right, 1 minus T2 for a Carnot engine, 1 minus T2 by T1 is equal to 1 minus Q2 by Q1. Okay, or right, Q2 by Q1 is equal to T2 by T1, or right, Q1 by T1 is equal to Q2 by T2 for a Carnot engine. This is what we have observed. Okay, or Q1 by Q2 equal to Q2 by Q1 equal to T2 by T1. This concept has led Kelvin to define what is known as Kelvin scale of temperature. That also we have seen in Carnot engine. Okay. Now, Cardinal Theorem says what? Okay, Cardinal Theorem says the first part of the statement is like this. Okay, Carnot engine working between two temperatures, right, that is higher temperature T1 and lower temperature T2, has highest efficiency. Okay, for a given two temperatures, right, the Carnot engine or reversible engine has highest efficiency, right, and no irreversible engine working between the same temperature limits can be more efficient than a reversible Carnot engine. That's how Cardinal Theorem goes on. Okay, that is, you fix any two temperatures. Okay, the reversible Carnot engine working between those two temperatures has highest efficiency. That is about Carnot engine. Carnot engine will have maximum amount of efficiency. Second one, no irreversible engine working between the same two temperature limits can be more efficient than a reversible Carnot engine. Okay, what does that mean? If it is a reversible engine, 1 minus T2 by T1 is equal to 1 minus Q2 by Q1. So Q1 by T1 equal to Q2 by T2. In general, for an irreversible engine, how do you write the efficiency? Eta irreversible is equal to 1 minus Q2 by Q1. Whereas eta reversible is, for reversible engine like Carnot engine, efficiency equal to 1 minus T2 by T1. Okay, no irreversible engine can be more efficient than a reversible engine. That is what is Carnot Theorem. That is, eta can be more efficient than means it will be less than or equal to, right, eta reversible. This is the statement of Carnot Theorem. Okay, no irreversible engine can be more efficient than a reversible engine working between same temperature limits. Okay, that is, eta irreversible is less than or equal to eta reversible. Okay, now what is eta irreversible in general? Okay, eta irreversible in general is 1 minus Q2 by Q1. Okay, 1 minus Q2 by Q1 is in general efficiency of any reversible engine. will be less than or equal to the efficiency of a reversible Carnot engine, that is 1 minus T2 by T1, or 1 minus Q2 by Q1 is less than or equal to 1 minus T2 by T1 means, okay, Q2 by Q1 is greater than or equal to, right, T2 by T1, or Q2 by T2 is greater than or equal to, right, Q1 by T1. This is the case of an irreversible case. If equal to sign is there, it becomes a reversible engine. If really the engine is really irreversible engine, Q2 by T2 will be greater than Q1 by T1. Okay, this is the consequence of Cardinal Theorem, we say. So in general, for any engine, okay, right, Q2 by T2 is greater than or equal to Q1 by T1. If it is an reversible engine, equality sign is applicable. If it is an irreversible engine, Q2 by T2 is greater than Q1 by T1. Okay. With this, now we'll see the application, we'll further enter into what is known as entropy concept. Okay. Right now, in entropy concept, you take a Carbonyl engine like this. Okay, source at high temperature, a source at high temperature T1, a sink at lower temperature T2. Okay, what does a heat engine do? Heat engine takes Q1 amount of heat from a source at higher temperature, does some W amount of work, and rejects some Q2 amount of heat into a sink at lower temperature. This rejection is a must according to second law of thermodynamics. Okay, right? Every heat engine has to reject some heat or the other into a sink at lower temperature. Without rejecting any heat, no engine can take some heat and convert all into work. That is nothing but Kelvin-Planck statement of second law of thermodynamics. Okay. Now, this is what a heat engine does. Now, what do? I will take this source, or what you call heat engine, as my system. Okay, source and sink are what you call surroundings, because our engine is interacting, taking some heat from the source and rejecting some heat into the sink. I take source and sink as the surroundings and heat engine itself as my system. Okay. Now, what happens here? System is taking, right, Q amount of heat from a sink source at higher temperature. So when you are taking heat from a source at higher temperature, what will happen, right? The source entropy decreases. What is the decrease in entropy of the source? The decrease in entropy of the source is Q amount of heat is being taken out of the source at a constant temperature T1. So decrease in entropy of the source is Q1 by T1. Q1 by T1. This is decrease in entropy of the source. Okay, let us call, I will give some numerical value to this. Let us call it as 10 joule per Kelvin. 10 joule per Kelvin is a decrease in entropy source. Now, heat engine takes that heat energy, does some W amount of work, rejects some Q2 amount of heat, right, and goes back to its initial state. Going back to its initial state means what? Entropy is a point function or a state function. That's what we have seen in our last video. Right? Means, well, if you start from one point, go through a series of changes and go back to the initial point, right? All point functions or state functions will remain invariant. Okay, that is, system's entropy will come back to its initial value. Change in entropy system will be 0. Now, one part of the surroundings, source is part of surroundings, their entropy has decreased. Now, what is happening to this heat engine? Heat engine is rejecting Q2 amount of heat into a sink at lower temperature T2. So, when you are rejecting heat into the sink at lower temperature, entropy of the sink will increase. What is increase in entropy of the sink? That is Q2 by T2. It is rejecting Q2 amount of heat into a sink at lower temperature. So, right, sink's entropy increases. Q2 by T2 is the increase in entropy of the sink. Means, now, heat engine is our system, source and sink both are our surroundings only. Meaning, one part of the surroundings has a decrease in entropy, other part of the surroundings has an increase in entropy. Now, because Carnot engine is a reversible engine, we have seen, right, Q1 by T1 is equal to Q2 by T2. Means, right, increase in entropy is also 10 joule per Kelvin. Means, in one part of the surroundings, right, entropy has decreased by 10 joules per Kelvin. In another part of the surroundings, right, entropy has increased by 10 joules per Kelvin. System's entropy has not changed. Surroundings entropy also has not changed. System plus surroundings is equal to universe entropy also has not changed. That is, in a reversible cyclic process. In a reversible cyclic process, change in entropy of the universe or change in entropy of system plus surroundings is always 0. Okay, that is ds, change in entropy, is equal to 0, we write, or circular integral, right, delta Q by T. is equal to 0, right? Circular integral delta Q by T is equal to 0 because system's entropy is not changing, surroundings entropy is also not changing. Okay, so I can write this Q1 by T1 heat rejected is Q2 by T2. Okay, because heat rejected, right, is known as minus Q2. Q1 by T1 minus Q2 by T2 is equal to 0, or Q1 by T1 is equal to minus Q2 by T2. Bring that Q2 by T2 to this side. Q1 by T1 plus Q2 by T2 plus Q3 by T3. Any number of cycles you take will be equal to 0, or circular integral delta Q by T is equal to 0, right? This is known as Clausius theorem. This is known as Clausius theorem. Okay, circular integral delta Q by T is equal to 0 is known as Clausius theorem. Next, I'll proceed in a reverse manner. Now I'll take the source, right, heat engine and the sink all put together as my system only in an isolated conditions like this. Means whatever changes that occur in the system will remain with the system only, right? There are no surroundings to my system here. This is an isolated system. Isolated system itself is equal to universe, we have seen in the previous videos. Okay. Now what is happening? Source is also my part of the system. Sink is also part of our system only. Okay. Now what is happening? From one side, whenever you take Q1 amount of heat at a constant temperature T1, one part of the system's entropy is decreasing by Q1 by T1. Okay. Right? And that heat is getting rejected into the sink, right? So what is increase in entropy of other part of the system? Q2 by T2. Okay, system, this heat engine is going back to its initial state. Change in entropy of this part is 0. Whatever is the decrease in entropy Q1 by T1 is equal to the increase in entropy Q2 by T2 here. That is, the entire system's entropy is remaining constant. Okay, there is no change in the entropy system. Entropy of the isolated system is remaining constant means entropy of the universe is also remaining constant. Either way, circular integral delta Q by T is equal to 0, we can write. Now, if it is not a reversible process, suppose say this is not a Carnot reversible engine, it is an irreversible engine, say. In an irreversible engine, what will happen? Okay, now take out this. Again, we'll go back to our heat engine and source separately. Okay, either way we can do it. This is our source at higher temperature T1. There is one heat engine, okay, doing some W amount of work, and there is one sink at lower temperature T2. Okay, lower temperature T2. There is one sink here. Okay. Now this is not a reversible engine, it's an irreversible engine, say. So system is taking Q1 amount of heat from a source at higher temperature, is doing some W amount of work, rejecting some Q2 amount of heat into a sink at lower temperature. Okay, what is decrease in entropy of the source? Decrease in entropy of the source is Q1 by T1. So let us say this is equal to 10 joule per Kelvin. This is decrease in entropy of the source. Okay, right? System does some W amount of work, rejects Q2 amount of heat into a sink at lower temperature. What is increase in entropy of the sink? Q2 by T2. Okay, Q2 by T2. Right? This is increase in entropy of the sink. Increase in entropy of the sink. Okay. Now engine is going back to its initial state. So all point functions remain constant. Change in entropy of the engine will be 0. Okay. So in one part of surroundings, entropy is decreasing by 10 joule per Kelvin. That is Q1 by T1. In other part of the surroundings, right, entropy is increasing by Q2 by T2. Now, in the earlier reversible Carnot engine case, right, in that reversible cyclic process, we have seen Q1 by T1 is equal to Q2 by T2. Okay, now what is this Q2 by T2? You see, according to what you call Cardinal Theorem, for an irreversible cyclic process, eta irreversible is, right, cannot be greater than, means less than or equal to eta reversible. That is 1 minus Q2 by Q1. Okay, is less than or equal to 1 minus T2 by T1. Okay, that is Q2 by Q1, because 1 minus Q2 by Q1 is less than 1 minus T2 by T1. Q2 by T1, Q2 by Q1 is greater than or equal to T2 by T1. Okay, or Q2 by T2 is greater than or equal to Q1 by T1. This equal to sign is applicable for reversible process. Greater than sign is applicable for irreversible process. Means for an irreversible process, Q2 by T2 is greater than Q1 by T1. Q1 by T1. Okay. Right, here we got this an irreversible engine. Q1 by T1 is 10 joule per Kelvin. Q2 by T2 is the increase in entropy. Q2 by T2 should be greater than Q1 by T1. Means what? If it is 10 joule per Kelvin, Q2 by T2 must be around some 12 or 13 joules per Kelvin, like that. Means what is happening here? System's entropy is not changing. Surroundings entropy at one place has decreased by 10 joule per Kelvin. At another place it has increased by 12 joule per Kelvin. That is, net surroundings entropy has increased by 2 or 3 joule per Kelvin. Okay, that is system plus surroundings entropy. System's entropy is remaining constant here, but surroundings entropy is increasing by some amount here. That is, universe entropy increases. Means if the process is a cyclic, if the process is a reversible process, system's entropy remains constant. If the process is an irreversible process, okay, entropy of the universe is increasing. If it is a reversible process, system plus surroundings entropy or isolated systems entropy or universe entropy remains constant. If it is an irreversible cyclic process, okay, systems entropy, system plus surroundings entropy or isolated systems entropy or universe entropy is increasing. Nowhere we will find in any process entropy of the surroundings plus system, that is entropy of the universe, never decreases. If it is a cyclic process, entropy will remain constant. If it is an irreversible process, entropy will increase. But entropy of the universe will never decrease. Okay, what is true for what you call the cyclic process is true for normal process also. If the process is a reversible process, okay, right, entropy of the system remains constant, entropy of this universe remains constant. Okay, that system plus surroundings entropy remains constant. Okay, if it is an irreversible process, entropy of the universe or system plus surroundings increases always. Okay, right? So, one important aspect of entropy is what? Entropy of the universe can never decrease. Processes are only two types, reversible and irreversible. If the process is a reversible process, entropy remains constant. If it is an irreversible process, entropy increases. But entropy of the universe will never decrease. Okay, entropy of the universe never decreases. Okay, that is one important consequence of what you call this. From Cardinal Theorem, we can arrive at that point. Okay, right? That is Q2 by T2 is greater than Q1 by T1 for an irreversible cyclic process. Okay, right? Thus, now we can formulate. Okay, we are getting more insights into the term called entropy. Okay, universe entropy is nothing but system plus surroundings entropy. See, system's entropy may increase or decrease. You give some heat. Okay, here when you are rejecting heat into the sink's entropy is increasing. When you are taking some heat from the source entropy is decreasing. Means if a system is there, okay, if a system is there, some system, you give some heat, entropy increases. You take out some heat, entropy decreases. Okay, similarly, surroundings entropy also may increase or may decrease. But system plus surroundings entropy, that is nothing but universe entropy will either remain constant or it always increases. It never decreases. System plus surroundings means nothing but universe. Universe is nothing but isolated system. Right? Okay, means now if change in entropy is ds equal to 0 means what type of process it is. The system plus surroundings or universe or isolated system, ds equal to 0 implies the process is an reversible process. The process is a reversible process. Okay, ds greater than 0 implies that the process is an irreversible process. ds less than 0 is never happened. That is, this ds less than 0 is impossible. Right? Okay, right? Nowhere universe entropy or isolated systems entropy or system plus surroundings entropy can never decrease. If it is a reversible process, it remains constant. If it is an irreversible process, it increases. Okay, right? Individually, systems entropy may increase or decrease. Surroundings entropy may increase or decrease. But put together, system plus surroundings entropy either remains constant or increases always. That's how we should understand. Okay. Now again, we'll go back to the Karna cycle only. Okay, once I go back to Karna cycle, okay, what happens here? We have defined ds as greater than or equal to delta q by t. Okay, Equal to sign is applicable for reversible process, right? Greater than sign is applicable for irreversible process, we have seen. Okay. Also here, heat rejected into the sink, Q2 by T2, if I take this as negative, what do we get here? Q1 by T1 plus Q2 by T2. Okay, right, is equal to 0 we are getting, because Q1 by T1 is equal to Q2 by T2. Since heat rejected is negative, right, I'll take it as minus Q2 by T2, I'll bring it to this side, it becomes Q1 by T1 plus Q2 by T2 is equal to 0. Or circular integral delta Q by T is equal to 0 if the process is a reversible cyclic process. Okay, total change in the entropy of the system is equal to 0. Okay, right, now if it is an irreversible cyclic process, delta Q by T, ds is greater than delta Q by T. But for a system, right, as the process is a cyclic process, right, if initial entropy is S1, after going back to the same initial point, its final entropy also should be S1, so that ds must be equal to 0. ds must be equal to 0 means, for a system, what does that mean? Right, delta Q by T should be less than 0 if the cyclic process of a system is what you call irreversible. For an irreversible cyclic process, circular integral delta Q by T is less than 0. For a reversible cyclic process, circular integral delta Q by T is equal to 0. So if I generalize, right, for a system, we have circular integral, for a system, circular integral delta Q by T is less than or equal to 0. In this, right, the equality sign is applicable for reversible process. This is for a system. Okay, circular integral delta Q by T for a system is less than or equal to 0. Equal to sign is applicable for reversible cyclic process. Okay, I am putting what you call circle on the integral, means it is cyclic process only. If for a system, if the cyclic process is reversible, okay, delta Q by T will be equal to 0. If the cyclic process is irreversible, delta Q by T will be less than 0 in any way, because ds must be equal to 0. Because ds must be equal to 0 for a system, in a cyclic process, entropy should not change. ds must be equal to 0. But ds is defined as greater than delta Q by T. That is, delta Q by T must be less than 0. Okay, this is called Clausius inequality. This is called Clausius inequality. Okay, this is an important point from examination's point of view. Okay, in many exams it has appeared the question, circular Clausius inequality. According to Clausius inequality, circular integral delta Q by T is always equal to 0. Circular integral delta Q by T greater than or equal to 0. Circular integral delta Q by T less than or equal to 0. It is less than or equal to 0, remember, not greater than or equal to. Okay, right, this is called Clausius inequality. Okay, circular integral delta Q by T equal to 0 for a system, that is known as Clausius theorem. Okay, when we generalize it to both reversible and irreversible process, we will get less than or equal to 0. This is known as Clausius inequality. Okay, right? So this important point from exam point of view, remember this. Okay, this is known as Clausius inequality. Now, entropy, again, going back to the physical significance of entropy. Okay, entropy is not a physical parameter, nothing physical about entropy here, because the change in entropy ds is being defined as delta Q by T, ratio of two parameters, heat given and temperature. There is nothing physical about entropy. Okay, it is a ratio of heat and temperature. See, we can feel pressure, we can feel temperature, we can feel volume. Okay, we can visualize internal energy. Right, but we cannot, what you call, there is nothing physical about entropy. Entropy is a ratio of two parameters, one is heat and the next one is absolute temperature. Okay, right, so because entropy has nothing physical to be shown and made equal to, people started visualizing, different scientists have visualized entropy in different manners. Okay, right, just like God or just like devil. Okay, when something is not physically visible, okay, what people let loose their imagination. Okay, they think that it should be like that, it should be like this, or that should be like that, etc. Okay, anything which is logical should be acceptable. Anything that should be acceptable. Same is the case with entropy also. Different scientists have visualized entropy in different ways. Okay, some defined it as what, some equated it to thermal inertia. Okay, some equated it to thermal inertia. Okay, so delta Q is equal to T into ds, right? Okay, See, the gravitational potential energy is what? Gravitational potential energy is mg into change in height is change in gravitational potential energy du is equal to mg into dh, right? Change in by what amount potential energy changes. It depends on the height through which it has changed. Its position has changed in height. Change in height. Okay, du. Similarly, that mg is ds is taken as entropy. Okay, change in height or right. Thermal inertia we call it. Temperature is equal to mg, some fixed property. Okay, this is heat energy, this is potential energy. So ds is equated to change in height. Change in height, if the mass is more, change in height will be difficult. If the mass is less, change in height will be easy. Similarly, right, entropy. Entropy is equated to thermal inertia. Okay, if system's entropy is more, it is difficult to change its thermal state. If system's entropy is less, it is easy to change its thermal state. Okay, so entropy is equated to thermal inertia. Some people equated it to unavailable energy. Okay, some people have equated it to unavailable energy. What is unavailable energy? Energy is there, okay, but energy which cannot be converted into useful work is known as unavailable energy in the universe. Okay, so if some system's entropy is more, people said that its unavailable energy is more, they said. Okay, system's entropy is less, unavailable energy is less, means energy which cannot be converted into work is known as unavailable energy. That is related to entropy, they said. Okay, next one. Some people have defined it as what you call as equated it to disorder in the system. Okay, entropy is taken as a measure of degree of disorder existing in the system. Okay, if disorder is more in the system, entropy is more, or otherwise. Okay, if entropy of a system is more means disorder in the system is more. Entropy system is less, disorder is less. Okay, so entropy is related to what you call degree of disorder existing in the system. Some people have equated it to our lack of knowledge about the system. Okay, lack of information about the system. Okay, our unintelligence about the system we can call. Okay, if system's entropy is more, our information about the system, our knowledge about the system will be less. If some system's entropy is less, our information, our knowledge about the system will be more, they said. Okay, like this, entropy has been given different interpretations. But remember, all interpretations lead to one and only one concept. Okay, entropy only, right? All are almost equal. Now we have to verify one after the other. What is entropy and disorder? What is entropy and unavailable energy? Okay, etc.